Okay. Good morning, everyone. I'm Srividya Subramanian. I work at the Max Planck Institute for Extraterrestrial Physics in Germany. I'm going to continue talking about astrophysics, but in a different perspective as a use case provider for the INODE project. I'm going to start my presentation with a brief overview on the major scientific problems existing in the field of astrophysics, followed by why INODE. Then I will introduce you to the database called SDSS that we have integrated with INODE. I will end my presentation with an example use case that we would like to probe with INODE tool. So, like any research field in the era of big data, astrophysics is no exception. It's flooded with huge amount of data from advanced observing facilities around the world throughout the year. Handling such data are extremely important in addressing the major scientific problems existing in the field. For example, how the universe began or how it will end, the structure of the universe, galaxy formation and evolution, and so on. Aim of INODE is to develop a comprehensive platform in which a user, who can be an expert or a common public, can extensively access the database in deriving new insights and in discovering new science. Such technologies are crucial not only to handle the currently available databases, but also in preparing us for the future surveys like DAISY, FOMOS, PFS, Euclid, and so on. Generally, astronomical surveys aim at developing a catalogue of all astronomical objects that one can observe in that particular region of the sky. Such surveys normally observe a few million astronomical objects and always comes with handy huge databases. SDSS, the Slovan Digital Sky Survey, is one such survey which started back in the year 2000. So we already have huge amount of valuable data taken over the last 20 years, and this is not the end of it. SDSS phase 5 has just started and we will be receiving huge amount of data in the near future. Over the 20 years, SDSS has produced the most detailed three-dimensional map of the universe that exists till now. So to give you a flavor on the number of records that INODE would be handling is of the order of 800 million in case of SDSS database. In any astronomical surveys like SDSS, astronomers do two modes of observation. One is the photometry and the other is the spectroscopy. In photometry, we take pretty pictures of astronomical objects in various wavelength region using filters that are sensitive to those wavelengths. Hence, here you see beautiful images of a spiral galaxy called the Whirlpool galaxy at radio, infrared, visible, ultraviolet and X-rays. Normally, astronomical objects emit light in the entire electromagnetic spectrum, and the peak emission depends on the temperature of the emitting source. Here you see cold gas available in the Whirlpool galaxy emitting in radio region, while the extremely hot plasma emitting in the X-rays. From images, one can derive physical properties, physical characteristics of the astronomical objects. For example, how bright it is in terms of magnitudes, how big the object is, or the structure of the emitting source, and so on. And such derived parameters are available in the databases and a photometric set of tables. Coming to the next mode of observation called the spectroscopy. We all know the famous prism experiment where prism disperses white light into colors from red to violet. In spectroscopy, we collect the flux emitted by the source in every wavelength in the form of a spectrum with a very high resolution. Spectrum comprises characteristic continuous emission along with the emission and the absorption lines. From these, one can infer many important properties of the emitting source. For example, temperature of the emitting body, metallicities, relative motion, or in case of galaxy, how they are in how far they are in terms of redshifts, stellar population, kinematics, etc. From the emission and the absorption line, one can derive many parameters. For example, the position of the spectral line, peak emission, or the equivalent width, etc. And these parameters are available under spectroscopic set of tables. Thus, from every astronomical surveys, photometric and spectroscopic parameters of millions of astronomical objects are available in those respective databases. One can do many scientific projects just by using those publicly available databases. I show you here one such example as an use case for the INODE project called the Green Pea galaxy. In this figure on the top left, you can see 3 consecutive images of Green Pea galaxy followed by a normal elliptical galaxy. As they are very compact, pointed and green in color, the name Green Pea. These are the famous set of galaxies discovered a decade ago in a citizen science project called the Galaxy Zoo. They are exceptional type of galaxies as they emit Lyman continuum emission, meaning they emit highly energetic radiation that can ionize the intergalactic medium 40 times bigger than the source itself. Such galaxies are extremely rare in the local universe that we see today, as the normal galaxies emit very little such energetic radiation. Hence, these galaxies are believed to provide an insight into a certain time period in the evolution of our universe called the Dark Ages. After the Big Bang, the universe was bright, hot and ionized, and later became neutral, cold and opaque, which led to the beginning of Dark Ages. During the course of a few 100 million years, formation of first stars and galaxies believed to have triggered the reionization of the cold neutral universe and led to the evolution of the current universe that we see. Thus, Green Pea provide a crucial insight into the evolution history of our universe. So far, only few hundreds of Green Pea galaxies are identified. When such astronomical objects are identified, it's a time consuming process for astrophysicists to derive all photometric and spectroscopic parameters meticulously and write extensive SQL queries in searching a database to find similar galaxies that share similar properties. But it's an extremely time consuming process, as I have already mentioned. With the currently available big data in the field of astrophysics, we need a tool like INODE, which would reduce all such complications and would allow us to traverse the database very efficiently using natural language and let us discover new science. Thank you all.